This movie is for geometry. This is learning target number 5 for unit 7. Learning target number 5 for unit 7. Similarity in right triangles. So the first thing I want you to do, I do want you to get this warm up. You're going to need a sheet of printer paper. You're going to draw a diagonal, and then you're going to label all the angles that you get here. This right here is an altitude, so you can construct the altitude, noticing that the altitude is perpendicular to the diagonal, going through this point. So you can construct this altitude, and then that'll separate so you get angle 6 and 5, 8 and 9 here, so on. So label those, and then I want you to cut these out so you've got your 3 right triangles. Once you cut them out, explain how you know that the matching angles are congruent. How can you match the angles? So you're going to rearrange them to show that all 3 triangles are similar. And then by what theorem can we say that the triangles are similar? Is it angle-angle similarity, side-angle-side, or side-side-side? Pause the movie, try this on your own, and then press play when you are finished. All right, if you rearrange them so that you have this smaller one on top of the medium one, on top of the larger one, you'll see that the angles will match up like this. So we know that 2, 8, and 9 are congruent because all right angles are congruent. They're all 90 degrees. And then 1 is congruent to 4, and 3 is congruent to 7 because they are alternate interior angles of parallel lines. See here, 3 congruent to 4, 1 congruent to 7. By the triangle angle sum theorem, then we know because we have 2 angles of one congruent to 2 angles of the other. 1 is congruent to 6 and 3 is congruent to 5. So that's a way to show that all 3 of these triangles, although not congruent, they definitely are similar. When you draw the altitude to the hypotenuse of a right triangle, you form 3 pairs of similar right triangles. So that's what we're looking at here in Theorem 7.3. The altitude to the hypotenuse of a right triangle divides the triangle into 2 triangles that are similar to the original triangle as well as to each other. So you can see the 3 similarity statements written here. Pause this movie, add this to your purple sheet, press play when you're finished. Let's identify similar triangles. We see here we've got one large right triangle, we have a medium right triangle, and we have the small right triangle, sort of like the Goldilocks right triangles. So the first thing, looking at this altitude YW, it forms 2 other triangles and we get 3 total. If we color code each one, so the smaller one here is blue, this medium one here is green, and then the larger is purple, we see that we get XYZ is similar to YWZ is similar, not congruent, to XWY. Notice that you need to have corresponding angles in the same position. Try this on your own. Write a similarity statement using these 3, and then try to write 2 different proportions using this ratio from your similarity statement. Pause the movie, try this on your own, and press play when you're finished. Okay, your similarity statement should look like this. Triangle PRQ is similar to triangle SPQ is similar to triangle SRP. These can be in different orders as far as which triangle you write first, but you've got to keep the order of the letters. Now if you have SR is to SP, you can set that equal to as SP is to SQ, and then SR is to SP as PR is to QP. You're aligning corresponding parts. Proportions in which the means, you have the means and the extremes, in which the means are equal occur frequently in geometry. For any 2 positive numbers a and b, the geometric mean of a and b is the positive number x such that, so this right here, the means, is going to be the same. So we've got a is to x as x is to something else. So this allows us to find a geometric mean between 2 values. Let's take an example. What is the geometric mean of 6 and 15? So we set it up 6 is to x as x is to 15. When we cross multiply, you notice you get a quadratic. You get x squared equals 90. There's no middle term, any x term, so what we do is we take the square root of both sides. X is the square root of 90, or we can simplify it to 3 square root of 10. So we say that the geometric mean of 6 and 15 is 3 square root of 10, or you can find the decimal. So the correct answer is B. Try this right now. What is the geometric of 4 and 18? Then write it down. You'll be asked to answer this at the end of the movie. In Got It Part 1, you used a pair of similar triangles to write a proportion with a geometric mean. You did short, long, short, long. This is of the green and of the blue triangle. If we look at this and we set up our similarity statement, we could see that short leg is to the long leg, as the long leg is to, short leg of this one is to the short leg of this one, as the long leg of this one is to the long leg of that one. When we cross multiply, we're really dealing with the geometric mean because SP is congruent to SP. And that's the long and short of it. Okay, not funny. Our corollary to Theorem 7.3 is that the length of the altitude, that is CD right here, to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. Looking at this example, we could see that 2 is to 4 as 4 is to 8. You can see here that 4, our altitude to the hypotenuse, ends up being the geometric mean. So 2 is to 4 as 4 is to 8. Pause this movie, add this to your purple sheets, press play when you are finished. Our second corollary allows us to see that the leg, either leg, in this case we're just looking at this leg, 2 is the geometric mean of the hypotenuse to the segment of the hypotenuse. So we say 1 is to 2 as 2 is to 4, or 4 is to 2 as 2 is to 1. Now we could also use the green leg over here, so you can see that written in this example. So you can use either leg. Whole hypotenuse is to the leg as the leg is to the segment of the hypotenuse, either with the green or the blue. Pause the movie, add this to your purple sheets, press play when you're finished. So here are the two corollaries written out in this example, where we've got a right triangle to begin with. We draw an altitude, create 2 more right triangles. We see that part of the hypotenuse is to the altitude as the altitude is to the other part of the hypotenuse. And then we also have the one with the legs that we just looked at. What are the values of x and y? In this example, I've got the 2 parts to the original hypotenuse, the larger triangle. So if I'm trying to solve for x, which is one of the legs of the larger, I would say that I can set it up this way. 4, the part of the hypotenuse, is to x as x is to the entire hypotenuse, 4 plus 12. So I do part right here. 4 is to x as x is to the entire thing, 16. Cross multiply 4 times 16, x times x, so I get x squared equals 64. I find out x is 8. In solving for y, I would do 4 is to y as y is to 12. I would use the other corollary, corollary 1. So 4 is to y as y is to 12, and I'm solving for y, and I get y is 4 square root of 3, or square root of 48. I would like you to solve for x and y on this example. Press pause, add this to your sheet so that you can answer this question at the end of the movie. Finding a distance. If we're looking at a robot, and you're preparing for a robotics competition using the setup shown here, points A, B, and C are located so that AB is 20, and AB is perpendicular to BC. Point D is located on AC, so that BD is perpendicular to AC, and DC is 9. You program the robot to move AD and pick up the plastic bottle at D. How far must the robot travel? So we would set this up. X plus 9, that is the entire hypotenuse here, is to 20 as 20 is to x. Cross multiplying gives me a quadratic. I get x squared plus 9x equals 400. I'm going to subtract 400 on both sides so that I get the quadratic equation equal to 0. This quadratic equation can be solved using factoring. It can be solved using quadratic formula as well. We've been practicing quadratic formula. Feel free to use that. If you factor, you would get this, x minus 16 and x plus 25. Solving would give you 16 and negative 25. Only the positive solution makes sense, so the robot travels 16 inches. If you use the quadratic formula, you should also get 16 and negative 25, and the negative doesn't work. Maggie has a kite with the dimensions shown below. What is the width of the kite? So if we're looking at the dimensions here, you can see that I have, even if we cut this off so that you only see this part, let me highlight what you should be looking at here. Let's say we've got this part of the triangle. If you look at this part, you see that we've got the big right triangle. This guy's 11, this guy's 25. And if we're solving for the dimensions of the width of the height of the kite, if we could solve for this guy, then we would know the width of the kite. So this is a problem that uses one of those corollaries. I want you to answer this question, and then you're going to put this in your movie put your answer at the end of this movie. And that is the end of this movie.